Hi everybody, and welcome to Lecture 1 in Real Analysis. To get things underway, we're going to go over a few definitions just to make sure that we're all starting on the same page, so to speak. First of all, we define the natural numbers, denoted with a bold-faced N. And since I can't write a bold-faced N, I'll denote it this way. The natural numbers are the set of positive whole numbers. 1, 2, 3, 4, 5, 6, 7, 8, so forth and so on. Now, I will say this about the natural numbers. Sometimes we stretch the definition a little bit. If it's convenient for our purpose, if it serves our purpose, and we don't contradict any sacred mathematical principles, sometimes we will allow 0 to be a member of the natural numbers. So whenever it suits our purpose and we don't commit mathematical heresy by doing so, we let 0 be an honorary member of the natural numbers. A situation where we might want to do this is if we're doing an induction proof and we want to prove that our proposition is true for n equals 0, 1, 2, 3, 4, 5. So instead of starting at n equal 1, we'll start at n equals 0. Now, this is the definition of natural numbers, but when it suits our purpose and we're not committing mathematical sacrilege by doing so, we'll allow 0 to be an honorary member of the natural numbers club. The second number system that we want to define is the integers, and it's denoted as a bold-faced Z. This is the set of all whole numbers, positive, negative, and 0. And we can denote the integers this way, or we can denote it this way. 0, plus or minus 1, plus or minus 2, plus or minus 3. Whichever one is more convenient and whichever notation serves our immediate need, that's the notation that we'll use. We'll look at a few more number systems now. The set of rational numbers denoted by a bold-faced Q. And I guess that's Q for quotient. I won't bet my life on it, but I suspect that's where it comes from. The rational numbers denoted by a bold-faced Q is the set of all quotients of integers where the denominator is not 0. So the rational numbers are the set of all quotients P over Q, where P and Q are both integers and Q is non-zero. And then we have the set of real numbers denoted by a bold-face R, and it's the set of all numbers on the x-axis. An alternate definition for the set of real numbers, the set of real numbers is the set of all numbers that have a decimal representation, period. And this representation may be terminating. Let's see, can we think of an example where the representation is terminal? 1.0, 2.56, 9.1. Okay, those are all terminating decimals. And notice that this is an integer as well. Non-terminating but repeating, so maybe 0.3333, the decimal equivalent of 1/3. And then we have non-terminating, non-repeating. Pi is one of those numbers. E is one of those numbers. Square root of 2 is one of those numbers. let's just make one up. Non-repeating, non-terminating, so let's say 0.1, 0.1, 0.001, 0.001. So what's going to come next? 0.00005, 5 zeros and a 1. Okay, there's no part of this decimal that repeats over and over and over again. It's a non-terminating decimal and it's non-repeating. So the set of real numbers can be defined as the set of all numbers that have a decimal representation. And the decimal representation could be terminating, like 1.0 or 2.5. Or it could be non-terminating but repeating, like 0.33333333. Or it could be non-terminating, non-repeating, like this: 0.1001, 0001, 00001, and so forth, off into the sunset. Okay, we've neglected one set of numbers that we're going to work with quite a bit. The set of irrational numbers. And there are a few ways of denoting these. We can denote them as Q complement. In other words, in the set of real numbers, the irrational numbers form the complement of the rational numbers. We can also denote the irrational numbers this way: the set of real numbers minus the set of rational numbers. And the set of irrational numbers is the set of all real numbers that are not rational. Every real number is either rational or it's not. And those real numbers that aren't rational we call irrational numbers. Now, an immediate consequence of this definition is the fact that the set of irrational numbers is the set of all real numbers that cannot be expressed as the quotient of two integers. So if a number is irrational, we can't write it as the quotient of two integers. And just for the sake of example, and we're going to be working with a lot of examples in this class, we're going to list some famous irrational numbers. Pi is a famous irrational number. E, the base of the exponential function, is an irrational number. Square root of 2 is an irrational number. And square root of n, where n is a non-perfect square. Let's see, will that fit in? Yeah, I guess it does. So, where n is an integer that is a non-perfect square, the square root of any n is a natural number. The square root of any natural number that is not a perfect square is irrational. We won't prove that. We will accept that as given in this class. We will show that the square root of 2 is irrational, and that's coming up in a couple of minutes. It's a nice proof, and it's a proof that we're all expected to know how to do. Okay, how do all of these things fit together? Let's let this big rectangle be the entire set of real numbers. Now, we just defined an irrational number as being any real number that's not rational. So that tells us immediately that the real numbers can be partitioned into two sets, two mutually exclusive sets whose union is the real numbers. So we have on one side the rationals, and on the other side we have the irrationals. So this whole thing, this whole rectangle on the left is the set of rational numbers. But let's see. Every integer is a rational number, isn't it? For example, 3, we can write that as the quotient of integers, can't we? We can write it as 3 divided by 1. So every integer is a rational number, because we can write that integer as itself divided by 1, the quotient of two integers. So inside the rationals, we have the integers, and then every natural number is an integer, isn't it? It's a positive whole number. The integers are the whole numbers, positive, negative, and 0. So that would include the natural numbers, wouldn't it? So inside here we have the natural numbers. And that's how all of these sets fit together. Now we're going to do the proof about square root of 2 being irrational. But before we do, we're going to look at a couple of definitions and a couple of lemmas just to facilitate our proof. Okay, even and odd integers. An integer n is even exactly when n can be written as 2 times k for some natural number k. And that makes sense because when we think of an even number, we think of a number that has a factor of 2. An integer n is odd exactly when n equals 2k plus 1 for some natural number k. So if we divide a natural number n by 2, we're going to have a remainder of 1. That means it's odd. And we'll denote the set of even numbers as a boldface E, and the set of odd numbers as a boldface O. That's as good as I could do. But these two sets, the even numbers and the odd numbers, partition the integers into two mutually exclusive and collectively exhaustive sets. Mutually exclusive, that means their intersection is the empty set. They have no elements in common. And collectively exhaustive, that means that collectively the two of them put together give us the entire set of integers. So what this means is that every integer has to be either even or odd and not both. Now let's do a few lemmas that we're going to need for our square root of 2 proof. The first lemma is that the square of an odd number is an odd number. So let me write this in an if-then form. Let me write this as a conditional statement. This is the same thing as saying if n is an odd odd natural number. Yes, I'll restrict the conversation to natural number here. If n is an odd natural number, then n squared is an odd natural number. So the equivalent of saying that the square of an odd natural number is odd is to say that if n is an odd natural number, then n squared is an odd natural number. So let's do the proof. Usually when I try to prove a conditional statement, I have no idea how to do it. Duh, what else is new? So what I like to do, just to sort of gain a little momentum, is to let the hypothesis be given. And here's my hypothesis. And of course, here's my conclusion. But because I have absolutely no idea how to do this, and I don't know what else to do, I'm just going to say, let the hypothesis be given. And our hypothesis is that n is an odd natural number. Okay, I wrote this down. I think I have a little bit of momentum. N is a natural number, so it's positive. And it's odd. All odd integers fit a certain form, don't they? All odd integers can be written as 2k plus 1. So n equals 2k plus 1. And I'll say for some natural number and here when I say natural number, k could be 0. So n could be 1, k could be 0. So here we're letting 0 be an honorary member of the natural number club. N is equal to 2k plus 1. Okay, I've done something with my hypothesis. Maybe I can do more, but at least I've done something with it. Now, let me take a step back and see what it is that I'm trying to prove. Because in all the excitement, I may have actually forgotten what my objective is. And my objective is to show that n squared is an odd natural number. Now, how do I do that? I don't know. But I do know what n looks like. So for lack of anything better to do, since I want to show that n squared is an odd natural number, I'm going to square n and just see what it looks like. If it doesn't turn out to help, it doesn't mean I did anything wrong. It just means that this was a good idea that just didn't pan out this time. But then again, it might turn out to be a good idea, so let's go ahead and do it. So n squared is going to be 2k plus 1 squared. And I'll square the first term, so that's 4k squared. And I'll square the last term, so that's 1 squared. And I'll take the first times the second, 2k, and double it. So that's what n squared looks like. Now, before I panic, let me take a look back up here and see what it was that I was trying to show. I'm trying to show that n squared is an odd natural number. Well, here's n squared right here. I want to show that it's odd, which means that I have to show that this thing looks like 2 times some natural number plus 1. Can I do that? I need to show that this looks like 2 times something plus 1. I can factor a 2 out of both of these terms, can't I? And that looks useful. This is a natural number. K is non-negative. So at the very least it's 0, but it could be larger. So let's say this, I'll call this M. N squared is 2m plus 1, where m is a natural number, and that could be m equals 0. So this implies n squared is odd. Now technically I'm done with my proof, but for the sake of my reading audience, I'm just going to restate what I've done. So if n's an odd natural number, that implies that n squared is an odd natural number. That's what I just showed. And I didn't have to put this last statement down here. I did it for my reading audience so that they'll realize that we have reached our destination. Sometimes we can follow each step in a proof and we go, yeah, that's right. Yeah, that's right. Yeah, that's right. And we check each step, but we don't look at the big picture. And when we arrive at our destination, we may not be aware of it. And in case our reader does this, we write this so that they'll look at it and go, n is an odd number implies n squared. Wait a minute. Yeah, that's right. This is where we started, and this is where we ended. Oh, son of a gun. Yes, if n is odd, that implies n squared is odd. Okay, now I see. So this last step is not obligatory, necessary in our proof, but we put it here as a courtesy to our reader just in case they've been reading the proof on autopilot This is sort of something that jump starts them and tells them, hey, we've reached our destination, time to get off the plane. Okay, let's take a look at what we just did. We restricted our universe to the set of natural numbers. So what we did essentially was say, let n be a natural number. If n is odd, then n squared is an odd natural number. What about the contrapositive? Let's see. Let n be a natural number. And if n is a natural number, of course, n squared is going to be a natural number. So let's see. We want the contrapositive. So we negate both of these, not P and not Q, and we reverse the order. So we want the negation of Q. And you know what? I guess I was too wordy here. This is not wrong, but it's not necessary either. We could just say if n is odd, then n squared is odd. So let's see. Negation of Q. If a natural number is not odd, then it has to be even, right? So the negation of n squared is odd is n squared is even. And the negation of n is odd is that n is even. Now, what do we know about the contrapositive of a conditional statement? The contrapositive is logically equivalent to the original conditional statement, isn't it? So I can say this. Since the contrapositive is logically equivalent to the original conditional, then we've already proved this statement because we've already proved the original conditional. So we've already proved this statement. If n squared is even, then n is even also. Now we got to do the other conditional statement. I'll show you what I mean. Okay, here's the other conditional that we need to prove. The square of an even natural number is even. Well, it doesn't look like a conditional statement, does it? So let me rewrite it. this is the equivalent. It's a conditional statement. Let n be a natural number. If n is even, so this is our hypothesis, then n squared is even. That's our conclusion. So we really are proving a conditional statement. As usual, I have absolutely no idea how to prove this. So for lack of anything better to do, I look at my hypothesis and I say, let the hypothesis be given. I'm just stalling until I get a good idea. And I still don't have a good idea. So I'm going to write out my hypothesis. And it's a good thing that I wrote out my hypothesis, because now that I'm looking at it, I can take one more step. I don't know where this is going to get me, but I can see another step to take. If n is even, then I can write it as 2 times some other natural number. So, all right, this implies n equals 2k for some natural number k. And here, we're not letting 0 into the natural number club. The natural numbers here will just be 1, 2, 3, 4, 5, so forth. So I know what n looks like. Now I guess it's time that I took a step back and I looked at what it is that I wanted to prove. I'm trying to prove that n squared is even. I don't know how to do that, but I know what n looks like. And because I need to show something about n squared, because I don't know what else to do, I'm going to take n and I'm going to square it and see what it looks like. Okay, so n squared equals 4k squared. I don't know what that does for me. So let me go back and take a look again at what it is I'm trying to show. I'm trying to show that n squared is even. Well, what's an even number? It's something that has the form 2 times some other natural number. Is that what this looks like? We can make it look like that, can't we? We can write this as 2 times 2k squared, and we'll call this thing m. And I'll remark parenthetically where m equals 2k squared is itself a natural number. Well, this is what we wanted to show, right? N squared equals 2m for some natural number n. So, n squared is even. We're done. But our readers who are looking at this proof on autopilot may not realize that we're done. So that we have to sound that gentle alarm that tells them it's time to get off the plane. And here's how we do that. We just tell them exactly what it is that we proved. And we say, if n is even, then n squared is even. Or I might write it this way. N even implies n squared is even. Now this last line is not necessary. I just write it here to wake up our readers so that they can verify that this is what we showed. We started out assuming that n is even. And here's where we wound up. We wound up at n squared being even. So now we're done. Proof done. Here's what we just proved. Let n be a natural number. If n is even, then n squared is even. We just proved a conditional statement. And here's our P. And here's our Q. Let's look at the contrapositive. Let n be a natural number. And how do we get the contrapositive? We negate each of these statements and then switch the order. So we negate Q. If n squared isn't even, it's got to be odd, right? So that's the negation. N squared is odd. And then we negate this thing. If n isn't even, then it's got to be odd. The negation of this statement is that n is odd. So we have not Q implies not P. So if n squared is odd, then n is odd. So we've already proved that. Now let's tie all of this together. So take any natural number n and take a pointer. If n is even, then n squared is even. If n squared is even, then n is even. On the other hand, if n is odd, then n squared is odd. And if n squared is odd, then n is odd. Now guess what? These two can be combined into one. n is even if and only if n squared is even. Okay? And guess what? These two can be put together to form this statement. N is odd if and only if n is odd if and only if n squared is odd. Now, maybe we didn't need to do all of this, but we needed some of it for our next proof. It's the proof where we show that the square root of 2 is irrational. Okay, here's our proof. As usual, I have no idea how to do this. And this is not a conditional statement. It's not one of those that we can write in the form of if P, then Q. I don't know what to do. And I can't stall for time by writing out the hypothesis and then seeing if maybe the hypothesis tells me the next step to take. There is no hypothesis here. So in this case, where I have absolutely no idea what to do, and it's not a conditional statement, so I can't put it in if-then form and assume the hypothesis, what I'm going to do is do the proof by contradiction. I don't know what else to do, so I'll try by contradiction. And I tell my reader that right off, just so that they'll know why I'm saying certain things. For example, I'm going to take this statement that I want to prove, and I'm going to assume exactly the opposite. Well, my reader might be puzzled why I would do such a thing if I didn't tell them ahead of time that I'm doing this proof by contradiction. Not only that, but I'm going to say it again. I'm going to say something like, suppose for the sake of deriving a contradiction, square root of 2 is rational. Okay. Well, where am I going to go from here? I guess what I'm going to do is I'm going to think about this. What do I know about rational numbers? Every rational number can be written as the quotient of two integers, right? Okay. So, and let me look in my notes. Did I use P or Q or M and N? I used M and N. Okay. And square root of 2, I do know that it has to be positive. Square root of 2 is somewhere between 1 and 2. It's positive. So not only are these going to be integers, they're going to be natural numbers. See, square root of 2 is rational, so it's the quotient of two integers. And since square root of 2 is positive, those two integers have to be the same sign. So I'll let m and n be natural numbers. Another nice thing about this, since I'm assuming that m and n are natural numbers, I don't have to stipulate that n is not equal to 0. If they're natural numbers, n has to be at least 1. Now, I actually did know how to do this proof. I lied. And I do know exactly how this is going to turn out. And if I don't take a clever step that somebody figured out years and years ago, if I don't take a clever step right here, I'm going to get myself into a situation where I keep going around and around and around. And the way that we prevent that from happening is we make an assumption on the natural numbers m and n. A perfectly valid assumption. I'll say without loss of generality. M and n are relatively prime. Now, we may know what that means or we may not. In case we don't, that means that m and n have no common positive factors or divisors greater than 1. Of course, they both have a factor of 1 or a divisor of 1. But we're assuming they have nothing larger, no divisor larger than 1. And this is a valid assumption. If these two things had a common factor, we'd cancel that common factor, and then they wouldn't have a common factor greater than 1. So let's see, what do I do now? I don't know. I don't know what else to do, so I'll square both sides. Two n squared is equal to m squared. In other words, m squared is equal to 2 times some natural number. So m squared has to be even, right? So m squared is even. And this implies that m is even. What do we know about even numbers, especially even natural numbers? We can write every even natural number as 2 times some other natural number, right? So this means that m is equal to 2k for some natural number k. And now, just so that it'll be easier to follow this proof, I'm going to call this thing equation 1. This equation, I'm going to call it equation 1. Let's see, m equals 2k, so I can have 2n squared equals m squared, but m is 2k. Okay, square this out, we get 4k squared, and we can cancel a 2 on each side of the equation. Now, where's that going to get us? N squared is 2 times some natural number k squared. That means that n squared is even, which implies that n is even. Well, let's see. That means m and n are both even, which means m and n have a common factor of 2. But this implies, no, this contradicts. This contradicts the assumption that what? M and n have a common factor of 2. This contradicts the assumption that m and n are relatively prime. Well, how did that happen? How did we get to the point where we got a contradiction? And let me say, I'm not upset about this at all. When we do a proof by contradiction, we want something to go wrong. We want something to go terribly wrong, and this is where it happens. We contradicted an earlier assumption. So this is exactly what we wanted to happen. Now we just have to find out why. You know, when a plane crashes, when an airplane crashes, the FAA sends out a team of investigators to find out why the plane crashed. This is what we're going to do right now. Why did this contradiction happen? Can only be one thing. The assumption that we made right at the beginning. We assumed that the square root of 2 was rational. So, since the assumption that the square root of 2 is rational leads to a contradiction. this assumption must be false. What assumption? The assumption that the square root of 2 is rational. So, square root of 2 is irrational. And that concludes our proof. By the way, welcome back to class. It's great to see everybody face to face, even if it's only from the nose up.